Okay, so let's get started. My name is Herminso Gómez from DICE. And let's see, I have some interesting topic for you today. It's improving 3D printing patient matched implants with 3D X-ray inspection and digital twin technology for metrology. That's quite a long title. I guess someone wrote that. Well, actually, it was me. It contains a lot of interesting technologies: 3D printing, 3D X-ray computed tomography, digital twins, metrology, and I don't know if I didn't have a space to put there artificial intelligence or something to include all the modern technologies. Here you can see some of the examples of how this technology is used in medical designs, especially for orthopedic implants. You can see examples of in the Journal of Quality Technology, because what I am going to talk today is mostly about how to do quality inspection. More examples of how this technology can be taken, the additive manufacturing can be taken advantage to build actual parts that can be used in medical implants. And this is probably one of the most successful stories of additive manufacturing. There has been a lot of hype on using additive manufacturing in safe critical components in aerospace and automotive, but it hasn't taken the predictions that were given back 10 years ago. But in the medical design for medical implants, it's already an adopted technology. Now, there are several places where you can see, for example, in materials and design, how this technology can be used on all the iterations that you have to do and quality that you need to do when you are building parts that go into a human body, especially for all the regulations that you get from the FDA. Additive manufacturing is great, and we love the freedom of degrees. So we say design comes for free in additive manufacturing, but it actually comes with a cost at the moment of quality inspection. And here are some of the issues. Yes, you have all the freedom to do all the imagination or design, or use your artistic inspiration, and all of that, but there are 4 fundamental problems. The parts are complex and they come in free-form shapes that are not easy to qualify. They are not the traditional parts of traditional manufacturing that you can inspect with perfect planes or spheres or cone or surfaces that are smooth. So it brings a challenge for the traditional inspection technologies. The surface has high roughness, and that's also a problem for, let's say, tactile probes that try to go and kind of map the surface, because it's going to damage the contact probe, and the scanning might not be as accurate. It also then has a lot of degree of freedom to design internal components. So it means you need to inspect this with something that can see inside, and sometimes in through metal. So vision inspection technologies cannot do that. Tactile cannot get inside unless they have an opening to get inside. So there are also internal geometries and undercuts that might be difficult to inspect. There also might be some voids, porosity, that need to be inspected, or particles that are left inside that you want to inspect and are not possible to see with visual technologies. So the options can be reduced to a few technologies, non-destructive. And you can see some of the challenges in some of the publications. For example, this author is highlighting how they can classify porosity, and they can access the features from different ways, but he makes this comment: the specimen had a quite roughness on the lateral surface, therefore the measurements with the caliper were different depending on where the caliper was placed. So that's a challenge. But there are many benefits of additive manufacturing, especially for medical design. when we want to include the benefits of bone adhesion to this type of metals, where porosity also is desired in the order of 75 to 80%, because it increases the fixation strength and promotes osseointegration. But there are limits on the pore size due to the biological factors. So pores that are larger than 700 micrometers can promote osseointegration, but reduce rates of volume of bone in growth. So we need to control that. And pore size less than 100 micrometers hinder growth of capillaries, and bone cells can reach and close pores. So we need to control the porosity that, and then we need some inspection technologies to do that. I'm putting here 3 typical examples of inspection technologies to inspect acetabular cups. Tactile coordinate measuring systems are great for inspecting dimensions, but I already mentioned some of the problems. CT, which is one of the technologies that I'm going to focus more on today, which can inspect porosity, thickness, coating, thickness of struts, cell distribution, cell size distribution, etc. And then we have light microscopy, which is also a really good technology. The only thing is you have to cut the part, you have to slice the part. Electron microscopy gives you even higher resolution, but then you have to prepare the sample to a small part that you, or a small cut that you can put inside of the system. Examples of how you can do that are in here, and you can see there how you can inspect porosity in the cross section. If you cut the part, might be some ambiguities of how you get the data depending of the orientation that you put in the light microscope of the cross section to put it in the electron microscope. So what are the options? There are several technologies that are also non-destructive, including ultrasonic testing that can see inside. So you don't need to actually section the part. But the one that gives you the most in terms of resolution and penetration depth is actually X-ray computer tomography. And from X-ray computer tomography, there are several technologies in different flavors that go from macro CT to micro CT or even nano CT. And they are dependent, or there is a trade-off between part size and spatial resolution. And I'll go a little more into that a little bit later on. And I give you why I'm insisting in X-ray tomography. Well, there are 3 main benefits. One, you can get the 3D volume, so you get the full volume reconstruction. Therefore, you can generate a digital twin, and you can use this digital twin to do further iteration of the design or do simulations. It's non-destructive, and it's complementary to other techniques. You can see on the end of the slide, this is an image of an electron microscope that is correlating with the 2 images over the left, my right. And those are actually X-ray computer tomography images. So what are the options when you go to X-ray 3D scan? The classical way is doing just X-ray computer tomography. You have a flat panel, an X-ray source, and you put your part or your component in a rotational stage to scan. That technology is great and is useful for most of the cases. One of the limitations is that it depends on geometrical magnification, and therefore you're limited in resolution for how close you can place the part to the X-ray source. Given that we are manufacturing parts of a finite size, then we are going to hit the limit of resolution depending on the size of the part. There's another alternative that goes around that problem by adding optical magnification with a set of lenses that collect the X-rays. They have a scintillator on top of the entrance surface, take the X-rays, convert them into light, and then go through a set of optical lenses, magnify them before going to the detector. And that way we can scan parts that are of a large size or even regular size, and magnified with the optical lenses. Each lens has a different scintillator that gives you a higher resolution depending on where you go, 4x, 20x, or 40x. Of course, there is a trade-off between resolution and field of view in that case. When you zoom in, you scan, like in a light microscope, a higher resolution, but it is a small section of the part. And this is the general workflow. You collect projections, a large set of projections. What did I do here? Then you go through the software reconstruction, get the 3D data, and once you have the 3D data, then you can go to the 3D reconstruction, either get a digital twin for doing iterations and improving in your design, or do a quantitative analysis of the porosity, for example. And why 3D X-ray microscopy? Because you have the ability to overload different scans. One full scan of the full part, and then zoom in with the optical lenses where you get higher resolution to see smaller details inside of the component. In this case, you see porosity and you see some surface roughness that is important for your materials. And you can scan for structural integrity, internal defects, porosity, and as I already mentioned, surface roughness. There is a little video here. Let me see if it plays. Yep, where it illustrates how you can get the different type of scan, different projections and different planes, where you can see not only the porosity, you can see inclusions, particle inclusions, and some powder of the material that wasn't melted during the manufacturing. And those are important things that you want to check when you do this. Because you have the data in 3D and you already have the digital twin, you can bring the CAD model, make a CAD to part comparison, and get a heated map with the deviations from the CAD against the actual part, and make your analysis. And if you are not happy with that, when you iterate the parameters of the 3D printing until you improve the manufacturing of your part. You also do reverse engineering and improve your process over time by, let's say, bring the initial result of your part after you scan, and you can see here the baseline had large deviations. Then you iterate your formula and do a new scan print the part, scan with the X-ray, and do the part to CAD comparison, and then you start reducing those until you hit the tolerances that are required for your particular manufacture. When you have the digital twin, you can use it also for simulation. If you simulate putting loads on top of the part, and you can do that from the CAD model. But the thing is, the CAD model doesn't tell you anything about, well, it tells you something about possible reality, but it's not the actual part. When you scan the part and you get the mesh, then you can do the image simulation, and yes, you can do it with the CAD simulation and compare if the results are giving you something that is similar. So you can choose the analysis data from your CAD design. Or you can start putting loads at different forces, and you can see in this simulation how it changes over the different time. So that's a way to use it. We've been listening to some of the previous presentations, how one of the main challenges of additive manufacturing is getting repeatability, making sure that you can reproduce the same part over and over again. And we have done some work in which you create a set of different coupons, and you can use CT scan to optimize this by checking after you have the X-ray CT, then you check the porosity, and you maybe do some metrological classification, and then you try walking back and see how you can improve, or what are the, after a set of variations of parameters, what are the optimal parameters to get the best dimensional accuracy and reduce the porosity in this given coupon. And in this curve, you can see that if you go to the parameters that are around here, then you get the minimum normalized porosity for that given part. and don't try to go all the way back there where you can see increased porosity. And you can map this in a three-dimensional graph where you play with the velocity and the power of the 3D printing to reduce this porosity. All right, so far I've been talking about all the things that you can do with the classical way of scanning and analyzing, which are the main topics I included in the title. But I was missing something, which is artificial intelligence. And I'm going to talk a little bit about that. But I want to be clear, I want to talk about a subset of machine learning, which is deep learning. So it's not generative AI. Oh, we don't want that. We don't want to generate fake data. We want to help the help from deep learning to train models, to reduce noise, and get better data. So one of the challenges when you use high resolution data is that the noise increases, and the noise increases because the level of projections that you need to take, generally we're talking in the order of 1,000 projections or more, and there is an analytical way of reconstructing data for CT in 3D created in the 1980s. It's an approximate algorithm and it's really good, but you need a large set of projections, and you still suffer of something that is called aliasing if you reduce the projections, or noise added to the data. So what we can do with deep learning is train a model when you get this high resolution data to recognize what is noise and maybe some of the artifacts from aliasing and get rid of them. And here is a comparison of the conceptual comparison of the two different ways of reconstructing. This is the classical way. You need a large set of projections if you want high quality data, but then the problem is you have slow scan times. An alternative to that is, let's see if we can create a model that can read what is noise and see what happens when you start reducing the projections and get rid of it to get a better image and faster scans. And we've been doing that. And here are some examples. This is the standard reconstruction. You can see that we really need over 1,000 projections in the classical way of reconstructing, and still you see noise on it. But you can recognize the features. If you reduce the projections to the hundreds, 400s, then you start seeing a lot of noise. So it's very hard to identify features from noise. If you use deep learning and you train the model to recognize what is noise and then get rid of it, but don't get rid of the features, then you can see that you preserve small features, even those small particles that are around the surface or small voids are still preserved while you get rid of the noise. And this is with the full set of projections. You get best image quality, but you can even do it faster with deep learning, because that set of data that was trained with deep learning is also even better quality that, in terms of image quality than the ones that you do with the standard reconstruction. So that's how we can take advantage of the deep learning technologies. And there are different flavors to do that. There is one that is we call it deep recon to do the actual 3D reconstruction, but there is another one that is called deep scout, which is what happens if I train a high resolution set of data in a small field of view and now try to use that model to expand to a low resolution in a larger field of view to recover resolution data from this. This can be also, because with the speeding time, we can take advantage from doing in situ testing. When you have these coupons and you load different force or weights, and if you try to do this with the traditional way of scanning, it's going to prove too long, so you have to do a discrete sampling of the data. But if you use deep learning, then you can have more data in less time, and then you can fill all those points in between to see the curve. So what you can see here is data from FDK, the green data, because you can only do 4 scans or to do 4 scans. Now if you can do a continuous or a more continuous sampling, then you can complete that curve and you reduce the time of scanning and increase the data that you can analyze. So that's how deep learning is going to help us. The second flavor, which I was mentioning, is okay, we have the ability to scan the full 3D data in a large field of view, but then there is a trade-off between resolution and field of view. You can zoom in with one of the lenses in a small region of interest, and you see great details, but then there is only a small region of interest. What if we can train the model in a small region of interest, collected at high resolution, then collect a low resolution scan, and then use this model to recover part of the data that you lost or is hindered by the resolution limitations, in this case, point spread function from optical magnification. And this is what is shown in here. And there is a comparison of what happens if you try to do Boyd quantification with deep learning and the FDK. The deep learning gives us access to higher resolution details, so you can see a larger level of porosity, not counting the fact that if you have noise included in the FDK data, then sometimes it's really painful to do this Boyd analysis because of the segmentation way that you have to do it, and the algorithm gets confused with what is noise and what is not. So let me try to summarize a little bit of what I have been showing today. I've shown how you can use modern 3D X-ray technologies to use it in 3D printing, especially for medical implants, because that's where we see most of the applications, physical applications nowadays. And there were, let me summarize in 3 main topics. The first one, I emphasize the main advantage of being a non-destructive inspection that can reveal the interior details of components. And what are the advantages as opposed to traditional ways of doing quality inspection? Visual, which have limitations because can only see the surface, or tactile, which also have limitations when you have a high roughness surface. You can see how can you use the digital twin, because when you scan the data, you actually have the 3D information of the data. You can convert that into an STL or a point cloud or whatever you need to compare a CAD, against the CAD model, or do a variations of printing parameters to optimize the recipe for the printing of your part that gives you the best quality. The last topic is how can we integrate deep learning algorithms into this quality inspection with 3D X-ray. What are the main advantages? And there were 2 different flavors. One, how can we improve the quality of the data by reducing the projections by using deep learning training models that go between the projections and the 3D reconstruction. And the second one is what happens if we try to use deep learning to train a model based in a high resolution scan in a small field of view, region of interest, and then propagate that model into a low resolution that captures a larger field of view and give you better data, which is of course, it will have some limitations if the part is not so homogeneous, but when the part has some similarities in material or composition, then this is a great technology to use. And I think this is the end of my presentation. If you have any questions, I'd be happy to answer.